Max Fasi from the University of Durham University. Moved there just a year ago.
Okay. Okay, thank you, Fran, and I'd like to thank all the organizers for inviting me to be here. It's always great to be back on the stage, and especially in such an occasion as this. So I will be, well, first one thing. So as you've heard, I was introduced as Max, but this is my actual name, and I was nicknamed Max on my first visit here to Manchester, and you can guess who did that nickname as a, well, not a, well, okay, I'll leave it there. So this is joint work with some Swedes. Okay, well, but
yeah, that's the same.
okay, yeah, well, I'm not the only person who got a nickname here, I'm sure. Okay, so this is a joint work with some Swedes. They used to be both at KTH, now only half of them are, and one of them has moved to Ericsson Research. Okay, so usually talks don't start with references, but in this case they do, and the reason why we're gathered here may or may not be the reason behind this choice. So these are two very influential books, at least for me in general, and for this very work in particular. They're a great book. The only thing I don't really like is that the A to width ratio is not the same, so they look slightly off in the slide, but they have aged extremely well. So this one is, I'll go here. Ah, thank you. So this one is 20 years old, and still, if you want to do something related to error analysis, this is the reference book, the one you want to look at. Yeah, I think the community has not felt the need for a new version of it. Perhaps a third edition will be due because of multi-precision at some point, maybe in a few years, I don't know. And well, this one is just a great book that I keep going back to all the time, and in particular for this work. So everything that we do stems directly from what is there, especially in the case of computation for this particular work that I'm going to present. There is one third book that I want to mention, and that's the one. I got this one, not this one really, but the second edition of it, because the third edition was not available yet. When I came here for the first time in Manchester, that was in 2015, and I came for a PhD interview, and I gave a talk, and this is what I got. And this probably tells you something about my skills at the time. Let's say at the time, I hope I've improved since. And there's plenty of very good advice about everything related to presenting mathematics and also doing research. But in particular, here I want to have a quote now about how to make good slides. And I don't know if I have to go here for sure. So does anyone know what these symbols here do? So we know that we should not keep them on slides, but does anyone know what they actually do? Yeah, so it turns out that no one knows. Like I tried Googling it, and so people say you should not use them, but no one knows what they actually do. So I tried it out. And so is this still true? I've never seen anyone using them.
I try to get a read of them very hard.
Okay, so okay, so probably for the first time this is about to happen. Okay, and this is the end of the funny part, and now let's start with the scientific one. Okay, so this will be a talk about matrix functions, and I left one of them here because I think this one may actually be useful. Okay, so this is a talk about matrix function. If you don't know what matrix functions are, this is the easiest definition in the easiest possible case. So you take a scalar function, so from C to C, analytical everywhere, and you just take the series expansion, like the Taylor expansion as it is here, and you replace the scalar variable by a matrix. And this is what you get. And this also gives you a very bad algorithm to compute such functions, and that is just a truncated series. So you take the first k terms, I call it tk here, and this is just because, well, I would be using this all the time. Yes, so this is just a polynomial in the matrix A. That's very easy to evaluate. But then the question is, how accurate is this? So if you've played with this kind of things, you probably know the answer already. I just want to show you in one long slide. So what I'm plotting here is the error. So I'm using a polynomial of degree 15 to fit the exponential. And this is the relative error. That's the thing I'm going to plot. So as you would expect, if you're very close to 0, then you are very accurate, but then exponentially fast, you get very inaccurate. So the thing here is, so this red line is the level of the unit round off for double precision, or binary 64 if you prefer. And as you can see, you are going very much lower than that. And I can squeeze everything along the imaginary axis so you can see it from the front. So essentially, when we are using double precision, we would like to be just below this red line. But here in the middle, we have a lot of extra accuracy, which we don't really need. But we would be very happy to trade off all this area down here for just a bit more at the edges. And this is what we are going to try and do. Well, try to do in this talk. Okay, so there are many ways in which you can evaluate matrix functions, and I'm sure your favorite one is not on this slide, but that's not a problem. You can go back to Nick's book for more, but here we are just going to look at the two first. So polynomials and rational functions. These are two classes of methods. And the reason why we want those is that they are extremely simple to work with. And that's because all polynomials and rational functions can be written by just combining three building blocks. Well, linear combinations, that's just what they are. A matrix multiplication is a product of two matrices, and matrix inversion is, of course, implemented as the solution of a linear system with multiple right-hand sides. But yeah, I mean, I'm sure I don't have to tell you this. I mean, it's just preaching to the choir. Okay, so then we want to go from this to graphs, and the way we do it is we associate to each of these operations, these three operations, three type of nodes. So each node represents a matrix, and then I use different colors depending on what. So the node itself is the matrix, and then the color tells you which operation is used to obtain these matrices. So if we do this, we can translate any polynomial or rational function to a graph. And so an algorithm that implements such a polynomial rational function becomes a directed acyclic graph. And computing the matrix function is essentially equivalent to evaluating the function underlying the graph. So I will use this notation all the time, this g of dot c. So the dot will be a matrix or a scalar, and c is just because sometimes I will want to do things with these coefficients. So c are it's just a vector that has in it all the coefficients of all the linear combinations in the graph. So what does a graph look like? So we have to start with an algorithm. Okay, so this is the first algorithm that you will find if you think about matrix functions and you try to understand how they work. So this is an algorithm for computing the most important, arguably the most important matrix function, the exponential of a matrix. So you use this identity. So instead of computing the exponential of A, you first scale the matrix, and then you approximate the exponential with a rational approximant. So this R of M is just a rational function of some sort. And then we have to choose somehow the degree of this function. We use this kind of target here. And then once we evaluate it, as is shown here, so just by solving a linear system, then we square a few times and we get the result, hopefully. Okay, so what does this one look like as a graph? We get something that looks like this. So we have a lot of nodes. So the identity and A are input nodes, so there's no operation associated to them. And then we combine this and we see we have a bunch of linear combination, the blue ones, then some matrix multiplications, the red ones, and there is only one inversion. There has to be at least one because this is a rational function. And yeah, so basically we can run the graph, follow the arrows, do everything that we have to do, and then eventually we can read off the result of the computation here. So this is an algorithm that works for scalars and for matrices, but now somehow we have to decide what M we want. This is the graph that corresponds to M equal 13. So it's an approximant of degree 13 followed by 5 steps of squaring. Okay, so how is it done in practice? Well, it's a bit technical, but so the idea is that we compute some quantity that is related to the matrix. Let's say it could be the norm, could be something else. And then we have a strategy like this. So if this quantity, whatever it is within this area with m equal 3, then we choose an approximant of the order 3. And then if it's outside, we try always to choose the approximant that has the lowest degree, because that's the cheapest to evaluate. And then we evaluate that one at that matrix. So how do we go from the matrix problem to a scalar one? I will use this one again and skip to the next one. Okay, so what we want to know is how far so let's say that we have a function f that we want to evaluate, and we use an approximant g. So what we want to evaluate is the distance between the thing that we actually want to compute and the thing that we are computing if we use this polynomial or rational function underlying the graph g. Okay, so we have bounds of this form. So here we compute the eigendecomposition of the matrix, and then we take the condition number, and we have a quantity here that is a scalar. Of course, in practice, we don't want to compute the condition number of the eigenvectors, and probably we don't want to estimate that either. But there are, of course, other techniques. So for instance, if you assume that the series expansion of f minus g is all the coefficients have the same sign, then you can use something different that depends on the norm of the matrix A. And then there are plenty of more recent and more advanced strategies that you can use to bound this quantity that we have here. So this f of A minus g of A, without computing either f of A or g of A. So something somehow cheap. You just evaluate these functions at scalars. Okay, so now we know how to go from matrices to scalars, and we can reduce the problem to a scalar problem. And now the next thing we want to do is we want to generate new algorithms based on algorithms that already exist. So the way we do that is we decide what our final algorithm should look like. So it is a polynomial, it is a rational function. So we fix how many nodes we are going to have, what kind of nodes there will be, so which operations and how they are connected. And then once we have that, we decide that we want it to be a good approximant on a disk. We decide somehow the disk. Currently, the way we do it is we try and we see what happens. So trial and error, I would say. And then we try to optimize the coefficients. So there are some coefficients we start with, and then we use some optimization techniques to get better coefficients, hopefully, if that's possible. That's not always the case. And to do that, we solve this minimax problem. So we try to minimize the maximum of the error on the disk. So, and then this C will give us the final algorithm, and I'll show you how. This is a very difficult problem, and we don't know how to solve it. So we try to relax it. And the first thing that we can do is we can assume that the function is analytic. So we can use the maximum principle to reduce it to a problem just on the boundary of the disk. So the maximum we know will be there if the function is analytic. But we still don't know how to solve this one. So we do something that any computer scientist would do. So we discretize this and we evaluate the function everywhere. And then we try to pick the maximum in this way. So we solve the problem somehow. And then our algorithm, so the algorithm that we've designed, will be just the function can be approximated to an extent as the function underlying the graph with these new coefficients that we have found in this way. So this could be a very expensive thing to do. We just have to do it once when we design the algorithm, and then we have an algorithm that we can run all the time. And we can just take this as sort of a building block. Sorry, it had to be here. This thing as a building block and put it into existing algorithms just as a replacement in a sense. How am I doing with the time?
You have time.
Okay, like 10 minutes or 5?
Slightly less.
Okay, 8. Okay, but thank you. Okay, so I'll skip this one, I think. So just the problem that in the end we solve is a non-linear eigenvalue, non-linear least square problem, and that's what we do, and we use Gauss-Newton to do it. Okay, so what is this optimization trick useful in any way? So here I have an iteration. This one is an iterative method for computing the square root of a matrix. Of course, an iteration in and by itself is not a polynomial or a rational function, but it is as soon as you sort of fix the number of steps that you want to carry on. So for 11 steps, for instance, we get a graph that looks like this. So we don't have any matrix multiplications, just matrix inversions. And of course, we always need the blue nodes if we want to do some optimization, because we need some linear combinations. That's what we are going to optimize. And so now I have the same graph as at the very beginning. So here on the left, this is the error if we just take 4 steps of the Denman-Beaver iteration. And this is, again, the relative error of computing z plus 1, the square root of it. And so you see it's pretty bad. The error on this disk of radius 1/2 is roughly 10 to the minus 6. But if we use the optimization, then we can get it down by quite a lot. This is order of 10 to the minus 16. It's not quite unit round off, but just over it. But this doesn't always work. So if instead of 4 steps of the Denman-Beaver iteration, we start with the polynomial of degree 13 that has the exact same computational cost in asymptotic terms, we get some improvement, but not quite as much. So here we have more or less the same error, 10 to the minus 6. We do the optimization, we get something slightly better. I think it's order of 10 to the minus 9, but that doesn't really give us some algorithm that we can work with. Okay, so we developed a toolbox in Julia to generate these graphs, do the optimization, and then also carry on some sort of backward error analysis to assess whether the algorithms that we get will give us what we expect also in finite arithmetic, because that's, of course, something that we want to know if we are to use these algorithms in practice. And then the most important part, I think, is the fact that we can generate C, Julia, and MATLAB code directly from Julia, and then we can use this. And we think that's one of the, well, it is done in a hopefully sensible way, so that we try to be performance aware. And well, you can see the code is available on GitHub, and this is also a Julia package that you can just install in the usual way from the package manager of Julia. Okay, so just one slide for comparison. We compare the optimized version of some state-of-the-art algorithms, so the exponential in MATLAB version that is just polynomial, this one, and then the Julia exponential. And these are some timings for 3 matrices. So we only put here the norm of the matrices, because what the matrices really are doesn't really matter. So we have timings and computational cost. So if you look at the columns, you see the time for a same. So this is all taken on the same machine. So it's we think as far as it can go in terms of comparison between different languages and environments. And so according to what we saw, the optimized version of Julia is always the fastest. So it's generally faster than anything else that we've tried. MKL is faster than OpenBLAST. I think there is nothing surprising there, because we were using an Intel machine. And this is also worth pointing out that here we managed to typically reduce by at least 1 the number of matrix multiplications that we need for a matrix of this norm. Okay.
So it's great to see Julia faster than C.
Okay, yeah, it is. So there is a reason for that, and that's we think that we are using in C calls to BLAS, but actually in Julia you can do this so basically you can aggregate many operations. That's the name for that. Eludes me now.
Yeah.
Okay, yeah, and so it does actually. That's why it's faster. So basically we don't do many calls to BLAS. Yeah. So that's there is an explanation. We are roughly sure that that's a good number. So yeah, dot fusion. That's the name of the thing that we can use. Yes. Okay, I think I'll stop here, and thank you very much.